Welcome all to your next set of notes. Today's notes are going to be on exponential and logarithmic models. But before we get into that, I want to run through one example, and I'm going to put a star in the margin of this because I guarantee you there's something like this on your next test. Very difficult problem, but it's something that we all can do. So we've got the logarithm of x plus 4 plus the logarithm of x plus 1 equals 1. We didn't see anything like this in our previous notes, so let's see what we can do with this. First of all, I've got two logarithms added together. We know from our previous work we can write this as one logarithm with the quantities multiplied. So we've got the logarithm of x plus 4 times x plus 1 equals 1. Now, from our previous notes, we know that the best way to solve a logarithmic equation is to write it exponentially. So we've got 10 to some power equals all this, and there's the power. So 10 to the first equals x plus 4 times x plus 1. And let's just clean this up a little bit. I'm going to use the distributive property here to figure out what this is equal to. So doing that gives me 10 equals x squared plus 4x plus 1 plus 5x plus 4. Now, if you recall these problems before, probably from your Algebra 2 days, but also earlier in this course, we know to solve this we need to set it equal to 0 and factor. Do not factor now, you'll just get what you started with. Let's set it equal to 0 first by subtracting 10 from both sides. And then we can try to factor this. So we get 0 equals, let's see, we know it's going to be x times x. We know two numbers that add to 5 multiplied to negative 6 are negative 1 and plus 6. Perfect. So now I can say either x minus 1 equals 0 or x plus 6 equals 0, which gives me an answer of x equals 1 or x equals negative 6. Seems good, and algebraically these two answers work. Now careful, if you plug these answers back in place of x here, try this out. Plug negative 6 in there, log of negative 2 plus log of negative 5. Guess what? You cannot take the logarithm of a negative quantity. So this negative 6 answer does not work. 1 you can plug in here, it will work just fine. So that is the answer. That's the only answer that works here, and we are good. Okay, so this problem here, like I said, very difficult. It kind of combines everything we've done in this unit so far into one problem. I guarantee you will see something like this on your next test. All right, so let's jump into new notes today. So exponential and logarithmic models. On our first day of this unit, you saw some equations like this. So this first equation tells you the amount of an investment, or the amount you have in the bank, that's compounded n times per year. So we've got the final amount, which is A, P is your principal, R is your interest rate, T is the time in years, and N is the number of times you get interest per year. If that investment is compounded continuously, your final amount equals the principal times e to the r times t, the rate times the time. Okay, so we're going to be referring to these. This first example, we're going to use one of those equations. Let's see here. If you deposit $5,000 in an account earning 8% interest compounded quarterly. So this is a very realistic type problem. You start with $5,000. So if you have $5,000 right now, you could put it in the bank. The bank will probably not give you 8%, but historically, 8% is pretty close to what the stock market will earn every year. Now, it's not a guaranteed every year. Sometimes you'll get 12%, sometimes you'll get 2%, but on average, you'll get around 7 to 8% if you're investing in the stock market. So kind of a realistic number. Compounded quarterly, that's 4 times a year. How much will you have after 10 years? So we're saying the amount we're going to have equals the principal, what you start with, times 1 plus the interest rate, again as a decimal, over the time, over the number of times you get it per year, which is 4 times, it's compounded quarterly, to the 10 times 4 power. Now your calculator can handle a lot of this. What I like to do is take care of that power first, and then I can type it right in my calculator. So if I've got 5,000 times 1 plus 0.08 over 4 to the 40th power, we can type that right in one line of our calculator. You'll get a final amount of around $11,000, actually $11,040, and I'm cheap, so I like to know how many pennies I have in there too, and 20 cents. All right, Now, the first problem, no problem. We can type that in our calculator. The second one, here's where things get difficult. In the above example, how long will it take you to double your money? So you saw that in 10 years, we more than doubled our money. How long does it take to double your money? Okay, so let's plug in everything we know. We know the final amount is going to be $10,000 equals the starting amount, which is 5,000, times 1 plus the interest rate over the times compounded per year, times the time per year, or to the 4n power. Now, if you didn't know a thing about logarithms, there would be no way to figure out this problem. What we have to do is solve for this variable here, and I put n in there. My mistake, I should have put t because it's the time we're solving for. So I'm going to go back and fix that and put a t in this spot. To solve for an exponent, the only way to do it is with a logarithm. Okay, so what we want to do is let's clean up what we can. First, we can divide both sides by 5,000. 2 equals, and then we can also figure out what this is in parentheses here. It's actually 1.02 to the 4t power. All right, we saw these in the last unit. To solve this, we need to take the logarithm of both sides, and you can use a natural or a common logarithm. And that'll allow us to take this 4t and move it in front of your logarithm. That gives us, we'll put it over here, the log of 2 equals 4t times the log of 1.02. Okay, we can now divide both sides by the log of 1.02. Now careful, don't just divide those numbers. These are two totally separate logarithms. So I get the log of 2 divided by the log of 1.02 equals 4 times t. So our calculator can handle this. Divide that quantity by 4, and we get the time it takes is, I should say, it's about equal to 8.75 years. So if you wait about 8 years and 9 months or so, you will double your money. So basically, thinking back to that stock market example, if you put money in the stock market, it'll double every, let's just say every 9 years or so. Now, the amount of money you put in there doesn't matter. Think about this equation. First thing we did was double by this amount. We ended up with 2 on this side. If you start with 1,000, if you start with 1,000,000, when you divide that out, you're going to end up with 2 on this side. So it doesn't matter how much you start with. The time it takes to double your money in the stock market is going to be about 9 years. And that's a generalization because some years do better than others. But in general, you'll double your money every 9 years or so. Okay, let's take a look at another example. Forget money now, let's talk population. So I'm giving you this model here. The population of the Earth in millions can be modeled by this equation. So population equals 4,450 times e to the 0.0173 t power. Now let's just go through some of the numbers here, talk about what they mean. That 0.0173, that's the growth rate. So it's like saying the population of the Earth grows about 1.73% per year. Since t equals 0 represents 1980, this right here is the population in 1980. That's your starting amount. Okay, so what will be the population in 2020? So let's figure that out. So the population will be the starting amount times e to the growth rate times t. Now careful, do not put this in place of t. If 0 was 1980, this is how many years past 1980? It's 40 years past 1980. So if we put a 40 in that spot, we should be good to go. Okay, so again, our calculator can handle all this. If you put what's up here in parentheses, you can probably type this all in one line, and you get Earth's population of about 8, it's going to give you a value of 8,889. Make sure I get this right, 0.8, which we can write that as 8.889 billion people. That's a lot of people. Now, I want to know, when will the population reach 11 billion? People who study this realize that, hey, there's only so many people we can have on Earth. At some point, we'll run out of food to feed them. We'll run out of space for everyone. If that value is 11 billion, when's that going to happen? So let's figure that out. So we want to know 11 billions, that's like 11,000 in this model, equals the starting amount times e to the 0.0173 times t. We want to know the time. Again, time is your exponent, so this problem is impossible to solve without using logarithms. So what we can do is divide both sides by 4450. If we do that, we get something around 2.47 is about equal to e to the 0.0173 times t. At this point, we need to take the natural log of both sides, and that'll move this power out in front. So I'm going to write this as natural log of 2.47 is about equal to 0.0173 t times the natural log of e. We know natural log of e is 1, so I'm going to disregard this over here and divide both sides by 0.0173. So we end up with t is about equal to, now careful, see that 2.47? Keep as many of those decimals on your calculator as you can. So if you can keep the whole works, if you can take the natural log of that entire answer, this will just make your answer that much more accurate. You'll get a t value, if you keep all those decimals, you'll get something around 52.3 years. If you got something different, it means you rounded differently. So I would recommend keeping all those decimal places when dealing with logarithms. Okay, so when is that population 11 billion? Well, that's 52 years past 1980. So if you take 1980 plus 52 years, that's going to be in the year 2032. So if we follow this model, in the year 2032, there will be 11 billion people on Earth. That is a lot of people. Okay, so now we know if we're given some kind of equation how to follow that to answer different questions. This next example, totally different. Now I'm saying let's find a model whose graph passes through these points. So let's say after 0 years, there's 7.24 million people in this country. After 10 years, there's 11.51 million. What's the formula for that? How do we find that formula? Well, here's a general formula for exponential growth, where A is your starting amount, B is your rate of growth. So what we have to do, like thinking back to your algebra days, we have to plug these points into this formula and solve for A and B. Always start with your initial point. So if we plug 0 and 7.24 in place of x and y, we get 7.24 equals A times e to the b times 0 power. Now here's why we always start at that point. B times 0 is just 1. E to the first power, or excuse me, b times 0 is 0. E to the 0 power is 1. So we end up with A equals 7.24. So now we've taken care of finding our first variable A. So let's, actually our first constant term A. So let's plug that in. Y equals 7.24 times e to the bx power. Now we're going to take our second point and plug it in. So we get 11.51 equals 7.24 times e to the 10 times b power. Okay, this looks similar to some things we've solved before. We're going to need a logarithm because what we're solving for is an exponent. But first, let's divide both sides by 7.24. If we do that, let me do that real quickly here. You get a value around 1.59 or so. And again, keep all those decimal places. So that value is about e to the 10b. Now we know we're going to need to take a logarithm of both sides. Let's use natural logarithm here. So we have the natural log of 1.59 equals, let's move that 10b in front, 10b times the natural log of e, which is equal to 1. If we divide both sides by 10, we get the natural log of 1.59 divided by 10 equals b. Okay, so if we take the natural log of that answer and keep all the decimal places you can, divide that by 10, you get b is about equal to 0.04, and I'm going to say 0.046. So that's your growth rate. So the population is growing at about 4% per year. So now we know A, we know B. Let's plug this into this equation. So y equals 7.24 times e to the 0.046 times x. And I guarantee you your next test is going to ask you to do one of these problems, so I'm going to put a star in the margin. All right, I have one final example. In your English class, you may have read some of Henry David Thoreau's work, and one of his probably his most famous work was Walden. He wrote of his time when he built his cabin on Walden Pond, and he did this in 1845. He wrote in there that the cabin cost $28.12. So he didn't spend much money. He's getting back to nature. He doesn't want to spend much on this cabin. I want to know if he did this today, how much would this cabin cost? So I looked it up. Since then, inflation has been going up at about 1.89%. So the amount, like if you bought a car at a certain point, inflation is just going to make it so that car would cost more down the road. Inflation's been about 1.89%. What would be the cost of building this cabin today? Well, let's just think about one of the formulas we had before. We can say the final amount equals the principal times e to the rate times time power. So even though this is used for a savings account, we can also use it to figure out the value of this cabin or what this would cost. So the final amount would equal the initial cost, $28.125, times e to the rate, which is 0.0189, times t. We need the time since 1845. Well, I'm just going to use 2013 as the year, and 2013 minus 1845, that's 168 years. All right, so 28.125 times e to this power here should tell us what this would cost him today. And it's kind of surprising. It would only cost him about $673.08 to build this cabin today. So like I said, Thoreau built this cabin on next to nothing. He really got back to nature. Really cost him only $670 some to build this cabin. Okay, that wraps up our notes on this unit. There's an assignment on page 232. Try some of these problems out. Let me know what questions you have before moving on to the next set of notes.